Hello everyone, you are watching Code with Shubhajit. Hope you are doing extremely well and let's get started with our problem. So today we have the medium level problem of lead code, which is search a 2D matrix. Let's go through the problem statement. So we are given an m cross n matrix and the matrix follows two properties, which are each row is sorted in non-decreasing order and the first integer of each row is greater than the last integer of the previous row. And we have, we are given an integer target. We have to say true if the target is there in the matrix, say false if the target is not there. So let's understand it, all the conditions here. So it's given that each of these lines, 1, 3, 5, 7, each of these individual lines, rows in the matrix, they are sorted. Along with that, the last element of this, 7, okay, is lesser than 10. The last element of this line, this row, 20 is lesser than 23. Okay, so this is also given. And as you can see, the target is 3 in this case and it's already present, so we have to return true. It looks very simple solution as well, right? But yeah, let's try to understand what's the brute force and what are the optimizations which we can have. The first brute force approach which is coming to my mind is, why not we will just traverse the array and find the target. So in our case, target is 3, right? So we can just traverse the array and like we can traverse this m is the number of rows and n is the number of columns. So we can have a double for loop. For I is equals to 0, I is less than m, I plus plus, and for this, for j is equals to 0, j is less than n, j plus plus. And whenever the ij, ARR of ij, let's say this is ARR, 2D matrix ARR. So whenever ARR of ij is double is equals to target, we will return true, and that's it. But you have to understand the time complexity for such scenario will be big O of m cross n. But don't you think that the situations or the constraints which are given to us, that each of these rows 1, 3, 5, 7, this one will be sorted, this one will be sorted, and this one will be sorted. Along with that, the last element, that is 7, is lesser than 10. Shouldn't we use these constraints? Definitely, we should. So there is one algorithm which I want to introduce to you guys, which is, okay, before telling that, I just want you to guess it. If anyone knows, and put them in the comment section, okay? We can know that how many people are actually knowing this from before. So the algorithm is binary search. Binary search comes whenever we have a sorted array, okay? So whenever we have a sorted array and there is something related to finding some element from the sorted array, the best approach should be a binary search. And how does a binary search work? Let me give you an example here. Okay, so this is the matrix, and what we have to do, we have to, let's say, find the element 11 in this case. We have to find the element 11. Just by seeing, you can see, okay, this 11 is there, but we can't just say 11 is there when we have to write a code for that, right? We have to devise an algorithm which will find for 11. So the first approach is like a linear search over all the elements, but in that case, we are not using the fact that this is a sorted array. So when it is a sorted array, we can have a pointer, let's say uh, I at the starting element and a pointer j at the ending element. Okay, we have this. So we will be running a while loop, and inside that while loop, we will be always calculating the mid. So what is the mid? The mid is I plus j by 2. So here what is I plus j? 0 plus 6. I and j are the index values, these 0, 1, 2. Okay, so 0 plus 6 by 2. What is 0 plus 6 by 2? It is 3. Okay, so 3, the third index. The third index is mid for us. We will check what the target which is given to us, right? Okay, first we will check, is 9 equal to target? No, 9 is not equal to target. Fine. So is the target greater than 9? Because if the target is greater than 9, then in that case, we don't have to actually search all of them because it is a sorted in increasing order. That's why whatever lesser than this element will need not to be searched if the target is already present after this mid element. Okay, so in our case that's only true because we have our 11 to the right of 9 because it is greater than 9. So what I will do, I will just increment my I to right of mid. So I comes here. Okay, now I will again, so my while loop will be running here and the while condition will be I is less than j, something kind of that I is less than j. because whenever I surpasses j, then in that case we don't need to run the while loop, because either the element was found if it has to be found, or else element is not there in the array which we are trying to find. Okay, good. So whenever I is less than j, again I will find the mid with I plus j by 2, and I will do the same thing. I will check whether at mid the element is there, whether the target is greater than the mid element, or whether the target is lesser than the mid element. Okay, so in this case 4 plus 6, 4 plus 6 by 2 is 10 by 2, which is 5. Okay, so 5 is the mid element here now. Okay, good. So is the target 11 is equals to the mid element? No, but it is definitely lesser than the mid element. Okay, so 11 is lesser than the mid element, that is 12. So now j will come to the left of I. Can you see now? I and j both are same now. So while I is less than j, this loop will break because I is now equal to j. So when it comes out of the loop, we will check the ith element. Does the ith element is equal to target? Yes, the ith element is equal to target. It means we have a target found inside the sorted array. And if it's not, then 11 is not there. Cool. I hope you are able to understand this approach, that how we are going to the left part when the target is lesser, and how we are going to the right part when the target is greater than the mid element. So in that case, it actually saves us a lot of time. It actually boils down the algorithm to big O of log n base 2. Why? Because we don't have to search the whole array. We just have to search one side of it every time, which actually decreases it to big O of log n. You can see any time complexity of binary search there, it will be explained. But for the sake of this problem, I will not be explaining how the log n is coming, but it will be lesser than big O of n, definitely. Okay, getting back to the problem. Now, if we have to find some target, in this case it is 3, and we know the fact that each of the rows are sorted, okay, then can't we do one thing? If we take this part as an array, this one 1, 10 and 23 as a linear array, if we see that as a linear array, 1, 10 and 23, okay, and if we try to search 3 here, if we try to search the target 3 here with the help of binary search, because these all will also be sorted in increasing order. Why? They all will be sorted in increasing order because we know that 7 will be lesser than 10. It means 1 will definitely be lesser than 10. 20 will be lesser than 23. It means 10 will definitely be lesser than 23. So 1, 10 and 23 will be in sorted order. That is the 0th column. So going forward with that and applying the binary search over this, we have this I here, we have this j here. Okay, I plus j by 2, the mid will be here. Okay, now we'll check, is 3 lesser than mid, equal to mid, or greater than mid? So yes, 3 is lesser than mid. So our j will jump down to m minus 1. So our j will be coming here. Okay, now the loop will break out. Why? Because while I is less than j is the condition, but here I is equals to j, so we will break. Now this is a very important part which you have to understand. After coming out, we will check the ith part. Okay, is the target. Now we are here not searching for 3 directly, because it might happen that 3 will be somewhere after this, after 1. Definitely, right? We are searching for 3. Whenever we came out, whatever the I was 1. Good. We will also check if I plus 1 is present, like 10 is present, right? I plus 1, the value is present, which is 10. I is 1, I plus 1 is 10. It means that there is a possibility that 3 can lie in between, or 3 can be present in the ith row. It can be a possibility. We can't be sure because we haven't traversed that part, but there is a possibility that it can be in the ith row, that is, for in this case, the 0th row. So we have to investigate further. Okay, so now we will actually discard these 2 rows because we know that 3 will not be present there, and we will only target this row after the first binary search. And here you can see that we can have a linear search and check that, okay, is 3 present there or not. Now when I say we can have a linear search, something should come in your mind. Why this guy is doing a linear search when he actually says that in a sorted array we can do a Binary search, if this comes to your mind, it means that you are trying to optimize the problem in your mind, and that's why it's coming. So this is a kind of a better approach, but it's not the most optimal approach. Okay, so here with this approach, what will happen in the row part? Okay, in the first column, which is the size of m, I have found out that okay, what is the actual row in which the value can be present. Okay, I found that, and after that I will be searching over n elements of that row which I have found in the previous step with a linear search and see that if element is there or not. If element is there, return true. If not, then return false. Okay, so this is one approach. There is one more approach which you might have thought about. Doing binary search over the first column to find which row we have to traverse, understand properly, and then again doing binary search over that row which we have found, whole row, and finding that the target is present there or not, just like what we have done here. So this thing will carry on after the first step, and that's what all the problem is. Okay, I will not be running the binary search again for this row because it is very much similar to here. Very much similar. What it is definitely the same as here, what I have explained. So after this, I will be going directly to the code and will show you how the things are done. Before that, just let me clarify that what will be the time complexity of this most optimal approach here. So for finding the row which we have to traverse, this is the first binary search which we will be applying, which is big O of uh, log m base 2. And when we found that row, we will again traverse it with the binary search, which is big O of log n base 2. So in total, it will become big O of log m base 2 plus log n base 2. And if you know a little bit of log and logarithmic rules, it's not the scope, but I will just tell you it is m cross n log base 2. Okay, now let's get to the code part. Okay, so to save time, I have initialized some of the elements which are required. So this is the answer which we will be returning, that is target found or not? That's the boolean value which you have to return. Okay, initially we have initialized it to false. One more thing we will check, that if the target is lesser than matrix 0 0, what is matrix 0 0? That is the first element. If target is lesser than that, then whatever we will search in this array, we will not find that target. So in that case, I will return false at the start only without looping through our logic. Now we will store the m and n as the matrix length, that is this 3 in this case, and n is matrix 0, that is the 0th row's length, which is n. So m cross n 2D array. Now we will be having two binary search. The first one will be on 1, 10, and 3. That is the first column of the 2D matrix. So I have taken the left as 0, and this is this left, and the right is m minus 1 because m is the size. So if the size is 3, the index of this will be 0, 1, 2. The index of this will be 2. Okay, so right is equals to m minus 1. And now I will start looping over this with the binary search algorithm. So while left is less than right, I will calculate what is my mid, which is left plus right by 2. And now I will check, okay, if my uh, matrix of 0, and why I'm taking 0, should I take 0 or not? No, I should not. This is 0, and this will be the row element. So row element is mid only. Okay, so this, if it is equals to target, then it's good. It means that we are able to find the target in one of these values in the first column only. Let's say if we have to search 10, then in this case this loop might have given us the answer. Okay, the first binary search loop only, but it's not currently. So we will see that if that is true, then if it is equals to target, I will return true. Okay, good. Else if the target is lesser than matrix of mid and 0, if that's the case, then what I will do, if target is lesser, it means that from the right element I will shift it towards the mid. So right is equals to mid. So you might be thinking that, okay, why it is mid, not mid minus 1? Because while explanation we have done that. So just a standard procedure, what we used to have in binary search, I'm just applying that. So the binary search standard algorithm is left is less than right. You can tweak it based on your need and based on the logic or the problem statement. But here, what I see was the left is less than right. This is a correct breaking condition in the while loop, and right we have to make it as mid. Okay, and whenever its target is greater than matrix of mid 0, in that case, but for the left part we will be making it to mid plus 1, because now the target is greater, so we have to go from, so we have to make the left to the right of mid. Okay, we have to go to the right subsection. I hope you are able to understand that. This is a standard of a binary search algorithm which I am applying. You can run more try cases and see that how these things are happening, and then you can understand why we have chosen these values. Okay, so after coming out of the loop, we will be having left, okay, which is very much important for us, because left is standing at a point which can give us a hint that, okay, it might happen that the row with the left or anywhere around that is actually having the element. Okay, so for that, what we need to check, we need to check that if target is lesser than matrix of left 0. What does it mean? I will explain you. Okay, in that case I will have to make left minus minus. So what I'm saying here, so I will explain you in the notebook. If let's say this is the first column, okay, I have changed it to horizontally, but let's say it is the vertical first column 1, 10, 15, 23, 32, and our target was, let's say, 17 in this case. Okay, so this is our I and this is our j. Okay, now for the first time 4 plus 0 by 2, which is this 2 only, mid. So we will see that, okay, target is greater than mid. In that case, I will be here, mid plus 1. Okay, nice. Now we will again do 3 plus 4 by 2, I plus j by 2, which is coming to 3 only. So mid will be here only. Okay, nice. As mid is here and 23, it is greater than the target, what will happen to j? J will become mid. So j will also come here. The loop will break because I is now equal to j. And after coming out, we see that we are present at a point that is, so in our case, this I is left actually. So we are standing at a point which is 23 and the target is lesser than that. So in that case, we have to make I minus minus. So the I was 3, I will become 2 in this case. Okay, in our case, left will become from 3 to 2. I have taken I and j due to simplicity. Okay, so this also needs to be done and checked. So that's why what I have done, I have actually checked that if target is less than matrix of left 0, please do left minus minus. Okay, good. So we have a left pointing row which has a chance of having the element. It might not also. So we will be having one more binary search loop for doing this. Okay. I have actually coded the second binary search part because now you have seen the first one, so it will be very easy for you to understand the second as well. Here, the left part we have taken as L, the right index we have taken as R, which is n minus 1. Why n minus 1? This is n, this whole thing. N is 4, right? 4 minus 1, 3. 0, 1, 2, 3, the last index of this for any row. Okay. Now the same thing, while L is less than R, we will calculate the mid, L plus R by 2. We will check if target is matrix left mid. So now left is fixed as the row and the column will change. But initially, the column was fixed as 0 and the row was changing. Okay, I hope you are able to understand that. Good. So when target is double is equals to matrix left mid, we will return true because we have found the element and it came just on the mid only. Okay, that's good. Now we will also check that if target is greater than matrix of left mid, if that's the case, we will make the left pointer to mid plus 1, else we will make the right to mid. Okay, like I also have realized this else if is not required because definitely this if and else if is running, it means this third will be definitely this case only. Okay, so I will just remove this part because it's redundant. Okay, after this whole while loop is done, we will be having this L pointer which is actually storing the point if the element is there or not. So we will just check that matrix of left, which is fixed, and the L, is it double is equals to target? Because if it is, then we will be returning true. But if it is not, then we are not able to find the element in the 2D matrix. That's very sad. We have run the whole loop and we are not able to find it. Anyways, the logic completes here and I have to run it. Sorry guys. Let me run it. I know it's a bit of a long video, but for explanation as well as the code part, this much amount it takes. So both the test cases pass. I will highly encourage you guys to have a dry run over some more examples. It will help you understand better. Submit the solution and see if all the test cases are passing or not. It's good to have you guys, and if you have any doubts, put them in the comment section. I will be really happy to help. That's all for today. All the best.